But let's talk about dark energy. So to be clear, dark energy is a placeholder for our ignorance regarding the cosmic acceleration. And then vacuum energy is seen as a natural candidate. But the problem is that it predicts these absurdly high acceleration rates.
That's right.
So is there another reason other than that the vacuum energy is canceled? So supersymmetry would say that the vacuum energy contributions are canceled. Is there another reason that the vacuum energy shouldn't even factor into the cosmological constant? Like it's a category error to think that we should be summing over bubbles.
The answer is we don't know. We don't know for sure. We don't really know. So even, for instance, if we take supersymmetry as an example, it is an amazing symmetry that would cancel the contributions when the symmetry is being satisfied. So it is very possible that we are the realization at high energy is supersymmetric. So if we discover new particles at the LHC or next particle collider or anything else, we will start seeing some signs of supersymmetry. That is still very much possible. And it is still very much possible that supersymmetry is being restored at a given scale. But the world that we're experiencing at low energy is clearly not supersymmetric. There's not a clear a partner for each for instance, boson, there's not a clear fermionic partner. So supersymmetry, the reality, it has to be broken below a given scale. This is observations. This is the reality of the world that we live in. So even if there were supersymmetry that would cancel all of the high energy contributions, the contributions from the particles of the standard model, so the contribution from the particles that we know we are made out of, electrons, the top quarks, the Higgs, etc., they should in principle lead to a contribution to the quantum vacuum energy, which is not cancelled out by supersymmetry. So there may be another symmetry out there, but supersymmetry is doing an amazing job at potentially cancelling out all of the contribution beyond, let's say, even TeV scale. But below that, we still need to face the fact that we have a leftover from the standard model, which will not cancel by supersymmetry. Now, it is a little tricky when we say the quantum vacuum energy of, for instance, loops of electrons lead to contribution to they interact with graviton and lead to quantum and it is a little bit tricky when we say that loop of the particles of the standard model lead to a contribution to the quantum vacuum energy. In fact, what we're doing there is compute some loops, which technically are infinite. And so we need to do a renormalization procedure. And if we do the most conservative regularization, if I do, for instance, what I'll call dimension regularization. So I'm not putting a cutoff at high energy. I'm not doing any of this. I'm just looking at how the contribution of these bubble diagrams, these loops, flows with energy. I see that for each massive particle, it leads to contribution which scales like the mass of this particle to the power of 4. And this is the most conservative way to do things. So it is still possible that we don't understand everything in this regularization and renormalization procedure. That is very possible. However, we understand this renormalization procedure extremely well for all sorts of other loops, which we then go and compute and compare with scattering processes at the LHC, and they give a flow and regularization scales of all sorts of different things, which we understand extremely well. So it is a little bit puzzling to think that we know so well how to compute those things, when gravity is not part of the game. And all of a sudden now all I do is I sandwich some graviton external legs. I don't need really to deal with quantum gravity in the sense of looking at an ultimate high energy completion of quantum gravity at or beyond the Planck scale. That's not at all what I'm doing. I'm just looking at a quantum effective field description of gravity, which we do on a daily basis. I do it on the board. And we do look for observations of that in the sky. We think we know very well how to do that. And yet, as soon as I start putting in some external legs, which are gravitons, so I want to look at the effect of this loop diagrams of, let's say, electrons on external legs, which are graviton, which in effect I'm wanting to see how this loop of electrons, loops of virtual electrons, for instance, lead to an effect, to an interaction with space-time. That's really what we're doing. All of a sudden, what we get as a result seems to be completely inconsistent with our observations. So probably it is true that something is going on there and we don't understand that so well, but it is very puzzling because everything else we understand it so well. Why is it the case that when I think of it in the case of graviton, that stops being so sensible? We don't know. The answer is we don't know. You can go into string theory landscape and think of there being a landscape of different possibilities where the leftover cosmological constant, the leftover vacuum energy could take many different values, and we just happen to be living in a realization where the leftover is just the right value, because if it wasn't that right value, we wouldn't be here to ask ourselves that question. That is always a possibility, but then it's a little bit unsatisfying because we don't know how to probe that possibility. We don't know how to probe alternatives to that. We're sort of giving up on trying to find a more dynamical, a more fundamental reason as to why the effect of all of the loops is not leading to what we would have expected.
Does philosophy inform your physics research? And by philosophy, you can count causality and thinking about lawfulness or the foundation of time into your answer.
Yeah. So those questions like causality, like unitarity, like the flow of time, that definitely informs all of our research, all of our results, all of the way we think about things. In fact, causality is really intrinsic to a lot of the questions that we're asking ourselves. So for instance, when we're looking at effective descriptions, effective quantum field theory descriptions for some phenomenon around us, we always want to make sure that they satisfy some basic criteria of basic, I would call them basic physics. You can call them philosophy if you want to. We would like it to satisfy some notion of causality. This is essential for us. And that manifests itself in many different ways. For instance, you can think of it, the notion of causality at zeroth order, you can think of it as saying, I want to end up with a phenomenology where I'm not able to go backwards in time and kill my grandfather so that I'm not there anymore. That's at the basic level. But in fact, when you represent that into a model where you think that Lorentz invariance is a fundamental symmetry, then that tells you that you shouldn't be able to have processes that go faster than light. In fact, it's not really that. It's a bit more precise than that. But we can embed those concepts into much more formal, much more rigorous ways to clarify how to move forward. There's no notion of unitarity as well, which in some sense is a very simple concept for us to think about. It's really to say that if I think of the possibilities of a different outcome, and so in quantum physics, we know that things are not deterministic. I can do an experiment over and over again. For each time, for each realization, I won't know exactly what the outcome will be, but what I know is what the probability of a given outcome will be. And so we are thinking everything, the realization is really very much into probability or amplitude of probabilities of different outcomes. But we want the sum of all of these probabilities to sum up to one. And we want those probabilities, these individual probabilities, never to be negative. So I want it to be a real number. And so that seems to be trivial statements. If I play the lottery, I shouldn't have more than 100% chances to win, and I shouldn't be able to have a negative chance to win because I can't quite make sense of that. This seems like completely trivial statements that guide our everyday life. In fact, is structural in the way we live our lives. If we didn't have this notion, then all hell will break loose. We'll be able to play the lottery over and over and over again and just take advantage of this. So it's sorts of sets up the structure of the reality in which we live in. And in the same way, this notion of unitarity sets up the reality of the physics with which we work, and so the models with which we work.
As you know, on Theories of Everything, we delve into some of the most reality-spiraling concepts from theoretical physics and consciousness to AI and emerging technologies. To stay informed in an ever-evolving landscape, I see The Economist as a wellspring of insightful analysis and in-depth reporting on the various topics we explore here and beyond. The Economist's commitment to rigorous journalism means you get a clear picture of the world's most significant developments, whether it's in scientific innovation or the shifting tectonic plates of global politics. The Economist provides comprehensive coverage that goes beyond the headlines. What sets The Economist apart is their ability to make complex issues accessible and engaging, much like we strive to do in this podcast. If you're passionate about expanding your knowledge and gaining a deeper understanding of the forces that shape our world, then I highly recommend subscribing to The Economist. It's an investment into intellectual growth, one that you won't regret. As a listener of TOE, you get a special 20% off discount. Now you can enjoy The Economist and all it has to offer for less. Head over to their website, www.economist.com/TOE, T-O-E, to get started. Thanks for tuning in, and now back to our explorations of the mysteries of the universe.